So we are starting this talk about machine learning projects. My name is Katya. I'm working for a Microsoft global team. We are helping people to build their AI machine learning solutions. Natalia?
And my name is Natalia, and I work in Microsoft Development Center Norway. Those of you who know that Microsoft actually have development in Norway, please raise your hands. Those of you who work there, please slow down your hands. Well, now everybody here knows that Microsoft actually have development in Norway, and we work on Office 365 products. And I work in machine learning and data science team, and we've been with Katya presenting for some conferences and meetups, and we noticed that there is certain interest to machine learning, and also got a lot of feedback that, okay, this is all cool, theoretical stuff, but what about real life? How do you run it? What do you do? What are problems? What is same? What's different? And that's why we decided to come out with this talk.
And share some experiences. So I want to start just a little bit from the slightly distance. So we are talking about artificial intelligence, machine learning, data science. Like people think that this is smart, we do with the data, some magic. And I just wanted to clarify those terms and to start clarifying what we're actually doing. So artificial intelligence is a field of research that is concerned about algorithms that perform tasks that are easy for humans but hard for computers, like vision, speech, creative work, art, thinking, communication. And that has appeared, I think, in the around 60s together with the first computers. And emphasize that I want to make here that artificial intelligence is actually concerned with any solution of that problem. So finding any solution that finds algorithm that would do something that human can do would be in the artificial intelligence field. So, for example, in the 70s, people talked about knowledge bases, expert systems, and believed that we build a lot of rules, then we'll solve the vision problem. In machine learning, in context, this is like, for us, the particular approach to artificial intelligence program. This is a field of mathematics that is helping to find algorithm with optimization methods from the data. And machine learning is proven to be the most successful approach to artificial intelligence problems, to find patterns in data, but machine learning can be used to find patterns in any data, not specifically for vision problems, but any data, IoT data, just lots of arrays. If it contains any pattern, we can use those optimization methods and find that pattern. As for data science, here we talk about insights of the data, about pre-processing, about data analytics. This comprises statistics and machine learning, and this is a lot about actually finding insights that not necessarily must contain machine learning solution. Like, for example, I have been at Evelina's brilliant talk about tab spaces and salaries. And we see a lot of insights and data using statistics. We don't have to use machine learning methods to find those insights. And data science project is a practice covering all activities to find these insights. So in this talk, we'll be talking about machine learning projects. And we think that it's basically built on 3 pillars, like data, model, and deployment. And we'll talk about all of them. And we'll start with data, because if there is no data, there is nothing to do with machine learning. It's just everything starts there.
Okay, so it's data. You probably heard it many times already. Data is new oil. What does it actually mean? What it actually means that data is a new resource which we need to take care of, which we need to understand, which we need to make money of. And data is a source of power. I think after Cambridge Analytica scandal, nobody questions any more power of data. This is obvious. But data is better than oil, much better than oil. Because if you think about it, oil is finite, it's limited. Once we will just run out of it. Data is infinite, it only grows with time. Then also, oil is very expensive to mine. You need to find a lot of scientists, so they locate where oil is. Then you build an expensive rig. It's a whole long process involving plenty of people and cost you a lot of money. Mining data is cheap. If you want to mine data, you can do it yourself. And then, of course, oil is no value after it's being used. But data only gains in value after being taken in use. When you start working it, the more you understand, the more it actually costs. So it's all about data nowadays. And if we have it, we need to do something about it. It's there anyway. So let's work on it. Let's locate it. Let's gain money out of it. Or in other words, let's mine it. In the same way as we mine oil, let's mine our data. Unlike oil, which is already big value in its raw state, data in its raw state actually has no much value. I'm not talking about personal data here. I'm talking like telemetry from devices, X-ray images in hospitals, or historical stock prices. Just by itself, it's nothing. But why else is data no value in the raw state? Well, first of all, we don't know where it is. It's spread around different databases, different logs, different files, maybe internet, plenty of data. So we need to find it first. Then, of course, even if we have it, we often don't know what's inside. We need to have a look to understand it. And sometimes it's so much of data that we cannot work on it without special tools. So data need to be collected, understood, and processed. And if you think about data, it's also need to be owned. It's kind of fun that only now we start understanding the value of data, because it can be stolen as well. I cannot skip not mentioning GDPR in this talk. So think about it. GDPR only comes now. Only now we are enforced to owe our personal data, and companies must fall in line. I started receiving, since 2 months ago, plenty of emails on every site I ever been and registered. They notify me about changing and handling my personal data. I think it's awesome. I think next generation will look at our times as we are now and think that we are some kind of digital wild, wild west. We have a lot of data, we have a lot of tools, generally no rules. It was fun, people, it's over. Welcome to next century. So where do we start? First of all rule of any project based on data. Crap in, crap out. Because data can be clean and data can be messy. To the left, you see what you usually get to work with. To the right is what you want to work with. And what is messy data? Well, data can be in different formats, in different time zones, it can be different encodings, it can be unstructured data. Data can be wrong or not reliable. For example, I collect my heart rate here with Apple Watch. Is it 100% correct all the time? You wish. Of course, there are wrong measurements. If I take my watch off, there is no information, which brings it to the next important point. You need to understand where your data come from. Look at those two charts. They're about the same range. What is it? Good? Bad? I have no idea if I don't know where the data come from. So the left one is the noise level in my apartment, a bit noisy. The right one is my resting heart rate, quite okay. So I want to bring to you, so without understanding the domain, you cannot achieve any significantly good results in your project. Invest time in understanding domain. But the most interesting thing I discovered when I started to work with data, data is alive. Data is like water. It's always moving. It's always changing. And it's a thing which requires continuous adoption. And that's also a thing which management or your customers struggle to understand. Because they are used to work on software projects, and how we did it before in software projects. We make a code, we deploy it, hey, we're done, move on. With data, it doesn't work like this. You write something, you deploy it, and then you start working, actually. So if I want to make a simple example, then expecting that your project based on data will not require any additional work after initial deployment is like buying your kid shoes and expect he will never grow. Also, I want to share with you that as you start working with data, you will have to share some progress. Situation, typical, lifetime. You get some data set, 3 days later your manager comes to you, is like, okay, how is it going? So, what's the progress? What are you supposed to say? I'm still working on it. I was like, I understand it better now than 3 days ago. That's no good. That's not going to go. So you have to share progress. And usually you share some analytics or observations or reports. And here is what you need to be aware of. Be very sure, 100%, at least 97% sure, that you know what you show. Because as soon as you're showing something, you will have to maintain it later. You will have to answer questions. Where is this come from? Where did that come from? And generally, in situation of exposure, your data always acts according to Zimmer's law, which is once you open a can of worms, the only way to recan them is to take the larger can. That means that anything I show, I have to explain, and I have to explain more and more as the day goes. The worst question I know, also the best, but also the worst, is why? Why did this metric drop from 70 to 68 last week? Let's say we have development teams, 5 development teams, contributing to the product. Product is collecting a lot of telemetry, and it all ends up in one metric which I show to management. Somehow, I'm supposed to know whatever happened. It can be true data change, it can be log format changing, it can be new data source provider changing, whatever. Looking for an answer is like looking for a cat in a dark room, and cat might not even be in this room. I'm the one who is asked, because I was the one who shown that number. So be aware, opening the can of worms, name it data reports. So if I want you to bring something out of remembering what to be aware of when you start working with data, is those 3 things. Crap in, crap out, no exceptions there. Data is no rigid matter, and then, of course, Zimmer's law. But let's say we have a data. We found it. What are we doing with it? What's next? How to bring value? Where is the business value? Katya will bring some answers.
That was pain. Now it's going to be fun stuff. So now we have the data, say, and then we have done all the painful work. We have cleaned it up. We have found all the sources. We have found everything that Natalia was talking about. Then we build a model. And the model, I think, is very most important part of machine learning projects. It's your success or your failure. It's have you found or have you not found a good model that finds the patterns in your data. So we can think about the model as like a new way of programming, like not when the human writes the code, but the program itself with optimization methods finds that code. So the model comprises learning algorithms and the data it learns from, and creates an artifact. And this artifact is created with a process called training. So depending on what data we actually have different types of learning. And I want to mention this because it's important. So if we have a labeled data, we are talking about supervised learning, about learning from the labeled data. And what is labeled data? Labeled data, when we observed some situation in the past that we want to predict in the future, we know the condition it happened, and that would be our labeled data. So for example, we can think about it as of X and Y. And as an example, who have not heard yet about house price prediction example in that room? Is there any single person? Everybody is aware about that.
Everybody is attending every single machine learning talk in this conference, right?
So everybody knows about house price prediction, right? Okay, who have heard about that? Okay, everybody. Then this is pretty simple. We collect the data about our house, about its size, about the number of bedrooms, some other parameters, and the price it was sold. And based on that number of bedrooms and the size, which is our X, we can predict what is the price we can sell it in the future. So that would be our label data. And I don't think I will be wrong if I say that vast majority of all successful machine learning projects is supervised learning. Because this is most efficient way of working with data these days. If you don't have labeled data, we speak about unsupervised learning. Here we just have some set of images without any labels, without any prior knowledge. And here we can do also analysis, we can do grouping, we can group that vectors, that data by similarity, but there's much less we can do. And sometimes it's very difficult to collect any data at all. For example, we cannot collect all the moves the helicopter does in the space, like all the moves like in the chess games. And in this case, we have other algorithms that called another actually learning type called reinforcement learning, where our algorithm actually learns from its own actions. And in a way, it's collecting data while it's learning. So it's very important to understand what kind of data you have. And sometimes it's just the best way is just to go and collect some data. We work with our customers in what is called Hackfest, when we sit down for several days and we solve certain machine learning problems. And sometimes we just discover on a very early stage, okay, we don't have enough data. We need to generate them. We need to go collect it, and we need to go to label that, instead of going another algorithm that would not be that efficient in that case. So when we understand what kind of data we have, we should think about what kind of algorithms we should choose about. And for supervised learning, there are two types of algorithms. It is a regression where we predict a value, like a house price. It's our favorite value we can predict in this conference. And, for example, classification, when we classify between cats and dogs on images. Or
yay, another obvious example.
Yeah, another example that we like very much. So for unsupervised learning algorithms here we speak mostly about clustering. When we group our data in certain clusters based on similarity belonging to that cluster. For example, we can think about customer segmentation. We look at all the customers and their buying patterns in the shopping center and see which of them are buying the same thing. So, or in some other way, behavior is the same or similar. And reinforcement learning is, it doesn't go into that umbrella like a supervised, unsupervised learning. And here we speak about algorithms that's called Markov decision process, which is allowing the algorithm to learn from its own actions, mathematically speaking. So that was about learning algorithms. And all these algorithms, they have a concept called training. And here is what it is. Training comprises three concepts that we should care about: objective function, loss, and the cost function. And objective function is something that we want to find, and that actually explains the pattern in our data. And our goal of modeling is actually finding that objective function that would fit our data set and that would emulate the pattern in our data set. Now, how we find that? For example, we have this data set, just one-dimensional. Then we make a guess. What function would actually describe that set of points? Anyone has a guess? Linear. Let's try. Like this.
It's a linear function. It's valid. You said linear. Here's your linear. Any problems?
It probably doesn't fit that well. Also, which parameters of linear function? It can be different parameters. So we don't know. We just select something random, something that we initialize somehow randomly. Well, maybe not zeros, because zeros will not allow us to learn, but something random. And but we want to find linear function that fits better than the one you see on the screen. And now it's actually in very luxury situation. We have one-dimensional x and one-dimensional y. We just have set of points. We can visualize it very easily. Imagine we have like 1,000 dimensions. Then we cannot visualize it at all. Then we just have to guess what kind of function it is. And then what we do when we made this initial guess, okay, then we calculate loss. It's the difference between our data set and the function. And then we calculate the cumulative loss. And we want this loss to be minimal and to be zero, actually. So we find such a linear function that fits better, for example, like that. Then the loss will be better. And so how we do that? We want this loss to be minimal. But there is no mathematical way to look at the linear function that we see and try to find a minimum. It doesn't have any minimum. But then what we can do, instead of looking at just the linear loss, we can look at the squares loss. And we look at this function that you see on the right. This function already has minimum, and it can be found using mathematical method called gradient descent. And this is the key difference between our loss that we calculated on the left and the function that is called cost function. So cost function has actually two characteristics. It describes our loss, and it has minimum, so it's so-called mathematically convex. And then we can use gradient descent method to find that minimum. So we just start from some random linear function, and then we calculate, and then we use gradient descent mathematical derivatives to a little bit correct it. So go a little bit better, and then a little bit better, like that. Like this is our initial function. And then with gradient descent, we find function that fits like that. That fits better than the initial one, because we use gradient descent, we minimize the cost function. Okay, then we can still think, maybe this is not that good. Maybe the loss is still high. Maybe we should get another assumption. Maybe this is a polynomial function, like that. We see it doesn't fit very well as well. But then, also using gradient descent and finding parameters, we can find some better function that actually will fit better our data set. So to find that function, this is the goal of our modeling and our training. So in here, I think important to say three things I wanted to emphasize. We can use gradient descent to find the parameters of objective function, but objective function choice is on us. If we have chosen wrong function, it will never fit. And also, we can program that automatically. It is just a loop. And also, many machine learning APIs like scikit-learn and TensorFlow, they have it already implemented. So basically, you call a function called fit or train, where a cost function is implemented, the training process is implemented, and you find your parameters for objective function. So that is very easy automated process. And this is basically, we write several lines of code if we use APIs, some more lines of code if we don't use APIs, but we still have it automatically. Our guess is only what objective function is. What else? I mean, can we use some fancy, very advanced cost function? And the answer is yes. And modern research in machine learning is actually publishes a lot about finding somewhat better cost function, someone for this particular data set that will, and then we'll have a better minimum and less training. So there is a lot of research happening about that, and sometimes it's worth just to look at that. But I think custom implementation of a cost function is quite rare. I think we do in reality.
Like, you don't really need it. You just stick to whatever is implemented in a framework and you're good to go. I had to implement it only once.
You once did it. I never done it, to be honest. So it's basically you select what is already implemented for you or what is already kind of state of the art. So sometimes there is some set of data that you really want to go and implement custom function that would optimize your algorithm. And then it's a very powerful thing to do. And I also wanted to talk about thing that is actually related to data, but more to model, about feature engineering, something that we do while we're modeling. Some features do not affect our model. For example, if we go to our house price example, then maybe the size of the house affects the price. Maybe number of bedrooms affects the price. Is color of my basement affecting the price? Probably not.
Unless it's yellow.
Yeah, I mean, people can repay. They don't care about it very much, I think. But we can figure it out. Maybe someone in some area, people are so much caring about the colors of their basement, so they'll just not buy the house that is yellow. That's probably possible. I doubt that. But I mean, these kind of things, if it's not affecting, then it's usually no harm. You just increase your training time. But sometimes you have features that are correlated. For example, you have size in square meters, square feet. And then you actually have double increase the effect of the size to the price if you're modeling like that. So these things that we should care about when we're modeling. What kind of features we selected. And sometimes people, they just select features by one, just remove them and see if it's affect our model. That exists in certain frameworks. So this is the whole process of exploration of features.
This is the most interesting process, I think, in the whole project.
You think so?
Yeah.
Well, yeah.
Okay, move on.
Yeah, it's...
Whatever.
You can argue that, right? I mean, important to talk with domain experts about it. Sometimes you have IoT data, there's lots of data, you have no clue what it is. But people working with this data, they understand. So, and they know, okay, just take this, you have 100 columns, take this 8. They will affect the result. That is very important to understand the domain. Well, otherwise, it's also possible to find out with mathematical methods, like removing features one by one and looking at features correlation and drawing the features and doing all this pain that data people do. So then we imagine we have our model. Then what's next? So we optimized it, we found the function, we minimized the loss. Can we use it? And when the funny thing, when I was doing my first machine learning model, I thought, okay, it's okay, we are done, we can just use it. What's next? But appears we have to do something. So we used all our data set just to find our model. We use the data we already have. We don't care very much about that data. We care actually about the data we haven't seen, about the data we already have. We don't want to predict anything on that. So this is not very interesting for us. For us, we are doing that because we want to predict the future. We want to predict something on the data that we haven't seen. And so here's what we do. We just split it. And we call it test data set and train data set. And we only use this part of the data to train. And we leave some part of the data that we call test data set aside. We don't show it to our model. It doesn't know.
And then it's got, surprise, new data.
Exactly, that's what we do. And then we actually run the model on the test data set and see how it performs. And so we see, like if we do regression, if we do value prediction, we just do certain metrics, basically. We predict mean squared error, just mean absolute error, just one parameter that, for example, in this case, is coefficient of determination. That should be close to 1 for a good model. For classification, we speak about number of true positives we found, number of false positives, number of precision and recall accuracy. Also, we should choose one number that we care about and then work with that. So if you're not happy, then you should go back and just build some new model and see how it actually performs on a test data set. So this has nothing to do with minimization. This is simple comparison of how data actually performed on the data that it haven't seen. And then it happens that we found it's not about that I was going to talk. Okay.
No, I want to talk about the size of test.
The size of split. The size, usually people leave like 30%, 20% of the data. Like we have 1,000 rows, 1,000 points, like you leave aside 200. But today, especially we use deep learning, we have millions of rows and millions of images that we train on, that we actually don't need to. We have 1 million, we have 200,000 for the test data set. And people have tendency just to use 1% for the test, and then they use all the data they have to train the model, and just have a little bit of the data to test, and that's enough. Given that is the same distribution that I'll talk about the data. Another thing that I wanted to talk about, that sometimes we found very good model on a test data set, like this.
On a trained data set.
On a trained data set, yes.
Yeah.
Did I say test data set? No, on a trained data set, yes. So with optimization, with minimization, we found very good model. And this is kind of every single point is on the line. So it's very complex polynomial, I guess. But would it actually fit a test data set? It's very unlikely, because in this case, we kind of overfit. We did it so well, but we don't care how it actually performs on a trained data set. We care how it performs on a test data set. We want something like that.
And I think human life example would be, you try too hard, guys. Relax.
Well, yeah, that's a good comparison. It's a good analogy. So then, and once we have the model, and once we have evaluated the model, and we see, okay, then 75% of my image is classified correctly. Is that good? Is that good or not good? Not good. And why not? Like 95%, is it good? It is good. No, it's not good, actually, in some cases. For example, if we go and do simple model that would predict 100 digits, that would predict how? 95%. And that's very no, it was 92. And this is very poor performance. Because if you try to analyze all of that, several of that such digits, that would be not good. But how we compare it with?
Oops.
Yeah. We can always compare with random. Like if you flip the coin, do we better or not? That's actually, I would say this is better than nothing if you have 5%. It would be hard to sell this model and using machine learning techniques just to do something a little bit better than flipping the coin. For example, tasks like computer vision, stuff that humans do very well. Like, for example, if we ask radiologists to analyze the pictures, and there is a lot of data about it, and people are very good at that. We can compare with that data. We can compare with human performance. Can our algorithms do better than doctors? That's legit in some cases. Or, for example, if this is not applicable, we can look at, okay, there is a state-of-the-art model. We can detect 100 digits with convolutional net with 99%, and then this is a good comparison we should aim to. If we have done something 98%, maybe it's bad, maybe it's good. So some published models that exist and people compare with. But when we compare, we should, and then when we test our models and when we actually use it in real life, we should be aware about the distribution. For example, I wanted actually avoid cat images, but I think in machine learning talk is always house prices and cat images. It's not evitable at all. So I have cat images.
Check.
Yes. So imagine we trained it on the cat from the left, which is very good high-resolution cat, and we want to test it on something, on cat images in dark and blurred and not in focus.
And it's also ugly.
I don't think it's ugly, it's just a picture because it was dark maybe and it was moving. But then if we will train our system with very good cat images and then we try to use it on these images on the left, we really don't perform very well on that model, because if you want to analyze that blurry images, then we should train on blurry images. And the same applies to lots of examples. For example, we want to predict the loan return rate, and we test the model on the people with high income. And then we are trying to use it on the people in different regions with low income. Then the model will not simply work. So we have to make sure that we are training it on the data we are going to use it, actually. So the final thing about evaluation, this is not an automated process. There is nothing we can write in a loop. Here we do every iteration, then we analyze how the model performs, and we do some changes, and then we come back to it until we are satisfied with our performance. So, not possible not to mention deep learning, I think.
Briefly.
So deep learning is like, it's very smart algorithm, neural network that we build, and it finds actually by itself the objective function in a way. And we can think about it like as a general feature extractor. So if nothing works, if we create a simple, fully connected network with like 100 neurons, or it should find the pattern if it's in practice exists. And if it doesn't, maybe it doesn't. Maybe we should go collect more data. So that is a technique I sometimes use. Deep learning is also like very much developed domain now. So there's a lot of networks that for different purposes published. People used months to train it, and they publish the parameters. And we can use transfer learning like to add some layers to it and just use it. And this is not requiring months of training.
Spending a lot of time there, and you just grab it and save a lot of money.
Yeah. So that's what intrigues what we are doing when we are modeling. And I don't know how much time you think it would take when we model.
I know how much time you take when you model.
I think it's the most fun part of the project.
Well, in real life, I would say on a good project, you will probably spend 5% of your time doing modeling. If you're lucky,
that's
maybe
not true.
4.
We should spend more on the modeling. Actually,
I can tell why.
Yes, we should spend a lot of time on the modeling. Basically, we spend a lot of time on data cleaning in practice. But modeling is very important. And actually, the goal is to find a model for our machine learning projects. But once we found it, we're not done, appears. We have to deploy it somehow.
Yeah.
And Natalia will tell about this.
Yeah. So it's important to remember that in the real-life projects, it's business we care about. And business understand one thing, which works end-to-end, and definitely, I'm sorry, not abstract model in a vacuum. So if you want it to work, let's say you have data, you have a model, what's next? How far are we actually from going into real life? Well, let's start from the first step you need, and it's data pipeline. Data moves inside systems and between systems. And data pipeline is a way to orchestrate those moves from source to final destination. And data pipeline contains all the steps which your data moves through with or without transformations on its way. Usually it's such thing as collection, cleaning, storage, analysis. It can also include training model. And what you want from your data pipeline to be, you want it to be reproducible, consistent, and robust. Reproducible means if you throw the same data into the same step, it should produce the same result. Consistency means if your format of data is changing, you need to change the script which is processing it. The simplest and always working way to achieve both consistency and reproducibility is to use good old source control. So we use it for all scripts. Whatever we can source control, we source control. And then, of course, you need robustness. That means in case of data pipeline meeting the data it haven't seen, maybe wrong formatted, it should not break. So we need to test it as well. As of experience, I can say we need to go and check our data pipeline all the time in case of some steps getting outdated or maybe not working, but we can't observe it. So in reality, data pipelines start looking like this after a while. So yeah, it requires as much monitoring and as much maintenance as the real pipelines. So I mentioned monitoring. I need to be very clear here. Whenever something goes left with your data, you need to notice it, and you need to notice it fast. Because a typical example is, okay, we need to retrain our model, and suddenly, oh, we have no data for the last month, because shit happens.
It's about can of worms?
No, we will get there eventually.
Okay.
So why would it happen? Let's say we have IoT device and it got disconnected. We didn't notice. Or we have a log format changed because a new framework came along and we didn't change some script version. So data is lost. You need to avoid it. So on top of your data pipeline jobs, you always need to configure monitoring and alert. So you can fix it, and you can fix it fast. Another thing which can help, you can always store your raw data for some short period of time. Short because it's usually a lot of it, and you cannot afford storing it for a long period of time. So when something happens, you have at least some time you can go and fix it and reprocess existing data so you don't lose it. And then, of course, reports. Reports is a heartbeat of your data-based project. And you need to implement it. And it's literally no limits how deep you can go into implementing reports. There is no limits how many insights you can bring from your data. But remember can of worms and Zimmergy law.
This is about can of worms.
Yeah, this is about can of worms. Be careful there. And also learn how to say no. Because people will come to you and they ask questions, and you might simply not have capacity in the team to answer it all. So you have to say, I'm sorry, I have to prioritize. I cannot do it for you. Yeah, that's necessary pain. Well, let's say you have a model. In terms of deployment, what we need to think about. Where do we store model? Who should have access to the storage? Does model have any kind of metadata? Version, when did we train it, how good it was, when do we plan to train it next time? Then how do we train it? Any scripts? We need to deploy them. Do we need to spin up environments? Do we have any scripts there? This is also part of deployment. Then do we have any quality monitoring of production model, which is if quality drops, do we have any alerts which will tell us your model is now crap, you definitely need a new one as soon as possible? And then, of course, you need to deploy the model, so you need some scripts there. Do we need to roll back to the old model if the new one suddenly doesn't perform? This is all part of deployment. And there are a lot of things you can implement, a lot of things you can automate. You don't have to do it all, but at least consider what is possible. What is it you can do? The better automated and better, of course.
But then if we talk about retraining, if we collected new data and we retrain, we can usually use the same model, which is retrain, and then with new data to new parameters, usually.
Usually, yes.
Sometimes you have to go back and say, okay, this data, it's just changed.
Yeah, sometimes it doesn't help. You run the same script, and then you can see that the data changed so much because data is alive. You remember that you need to go back and basically start modeling from scratch because the same feature they use, the same scripts, they don't work anymore. But that's kind of a version 2.0 of a product usually.
But this happens not so often. So often the data come from the same distribution, and if we just need to train it on a more recent data.
Yeah.
So and then we can just do it automatically.
And then, of course, I cannot skip such an important part of any data project, which is A/B testing. A/B testing is a way of monitoring the quality of your new model in our case. So we do it very simple. We take a group of users, try test on them, try the new model on them, and we call them group B, and then we compare how they act, how is the quality compared to group A, the guys who have no change. And I say compare. To compare, we, of course, implement some metrics. Choosing the right metric is very important because this is the single measure of how good your model performs. This is the number you report to your management. And in terms of deployment, what you need to think here, you need to design the right metric, you need to implement the right metric, of course you need to deploy, and you need to choose a/B testing framework. This is also on you. Next step, surprisingly, people think they don't forget, but they do. It's cost. People often think, okay, I know how much data I have, I know how much it will grow, I know how much storage it will cost me, and then they totally forget to think about read-write operations. And those can absolutely blow your budget. If you have a lot of heavy images and you have to read them every single time you retrain the model, you will just empty your budget immediately. So at the step of deployment, why I address it here, you actually start seeing how much things really cost you. And then you can start thinking of how can I optimize it. In case of images, for example, it might be very wise to pre-process them and store just features, which are much smaller. So every time you retrain your model, you work with pre-processed features and not need to read in all the images again and run expensive calculations. If training model is expensive, you need multiple GPU machines, maybe you don't need to train it that often. Think about it, compare it. So cost is at all times real pain in machine learning projects. So when you think about deployments, I want you to remember that you need to think of data, model, A/B testing, all continuously monitored, reported, preferably being aware of cost of operations at all time in a perfect world. So let's say we have it, model data, and we deployed it. But how do we bind it all together? What is the process? Because I assume most of people in this room are software developers, or at least worked in software developers. And software development lifecycle looks like this. We start with planning, analysis, and then we do design, implementation, testing, integration, maintenance. Machine learning projects are surprisingly different. This is a team data science project lifecycle. Doesn't look that neat, unfortunately. But we do start with business understanding, and then we move to data acquisition and understanding, then we do deployment and modeling, 3 pillars, you know. And all steps are kind of in an iteration in an agile manner as a software development, but they also interconnected. And when you have some sub-steps in a side just to make things look more complicated, like it's so very difficult. So let's start. In software project, we start with planning. In machine learning project, we actually don't have planning. Because when we have business idea, we have to go to data and think, okay, do we actually have data? Can we acquire data to answer the business question? Question can be, how do I attract new users? Or how do I make a better newsfeed? Or can be something like, how to predict cancer from CR images? Can be whatever, but it's always one single question. So you look at the data, think, no, it's not gonna work. Back to business, like, sorry guys, come up with new idea. Or you look at the data, think, oh yeah, okay, I think it's good. You go, start modeling, and it doesn't work. It's like performance is just out of hands. And then you either can go back to data and reevaluate it, maybe collect more, maybe just change features, or you go back to business and say, sorry guys, it's not gonna work. Or you can go back to business in a good case and say, guys, I have a better idea. I've looked at your data, we tried to model, and hey, we just can do it so much better. We can save you so much more money. So it's kind of, there is no single planning. The point is, you cannot commit to any kind of work in a machine learning project before you churn some data. But churning data is already work. So how do we do it here? Well, we do proof of concept. Right, Katya, you work a lot of proof of concept.
Yeah, basically all I do this because I don't feel the pain.
You work on the fun part. So proof of concept is a lightweight way to check if it's possible or not to answer the business question.
And toy data set.
Yeah, you take some small size data, you try to build some model on it, working, not working, rule of thumb.
Not necessarily small.
Not so big.
Well,
and then there is one big problem with new proof of concepts. I just want to share my pain. Management thinks that once we solve the problem on a toy-sized data, we're done. We know how it works. We just need to scale it now.
Yeah, this is the part when we found the model. What else we should do?
Just need to scale. Just, right. That's never how it works. Because working on a proof of concept, difference between proof of concept and a full-size integrated solution is as big as making dinner home or serve the same dinner on a day-to-day basis in a high-end restaurant to hundreds of people. Does it make difference? Does it make sense? I hope it does. So what do we do next? Let's say, we landed an idea, we have data, and in a typical software project, we do development or implementation. In a machine learning project, it's usually the pipeline, building pipeline, and the modeling. And that's the picture of how people think modeling looks like. We have some well-arranged data in a pipeline, everything works, and they do some magic in between, and hey, there's the model. Of course, it's not how it works. This is how it works. You have a lot of stuff in different places. You spend a lot of time building pipeline. Then you do mathematics and statistics. And then you have your model. Well, you have a model. You deployed it. Testing. Well, sorry, we really don't have testing. Well, we do have testing. But it's not like a well-defined step. It's like, now we test. No, we have data pipeline testing. We do test our jobs all the time. We have model testing, which is evaluation. And we have A/B testing. You see, they are kind of spread across all projects because it's data, model, and deployment. It's all over the place. It's not one single step. We have quality assessment due the whole lifetime of a project continuously. Integration is the next step in a software development project. Well, we have deployment and integration. I don't know, I talked about it already. I can only add one word. It's pain. Don't you ever underestimate integration time. Your machine learning solution is always part of a bigger system. Integration is inevitable. It's going to eat a lot of your time and space and pain and effort and whatever else I can mention. And then, of course, maintenance. Maintenance is maintenance. Inevitable. Well, bug fixes, apparently, as everywhere else. But in software projects, changes usually come from new requirements. In machine learning projects, they also come from true nature of data, which is changing. So sometimes nothing changes, but you still have to change something. So this is, again, data science project life cycle. I want to mention here an important point that there's some kind of same, but also very different. I hope it will help you to understand the difference if you start working on a machine learning project or if you work with machine learning project team, and let's say I am a developer, I'm in machine learning, and I use data telemetry produced by our team. It really helps a lot to communicate to them, to explain my needs. Fairly said, it takes several iterations to align, but that's the only way. So please communicate and learn how to explain things. It helps a lot. So as you can see, there is actually no magic. I think that's all we had to share by today, and we have some time left. So if somebody have questions, that's the right slide. Yeah. Questions. Okay, thank you.
Thank you. Thank you for coming here today.